So yesterday we introduced a particular result, apparently with no rhyme or reason, because we are just dealing with some result about differentiable functions or continuously differentiable functions, and we said that this will be eventually useful in deriving a certain form of the Euler-Lagrange equation apart from the one we have already seen so far. So just to recall, I don't exactly recall if I had mentioned this, but this was given to be the situation, right, for all g that was continuously differentiable. Now phi needs to be only continuous, not necessarily continuously differentiable, because if phi is also continuously differentiable, then it is incredibly easy to see that in view of this, with GA is equal to GB being 0, it is incredibly easy to see that phi must be a constant, because you can just differentiate this, no, phi g minus integration g phi prime, that must be equal to 0, and phi g evaluated at a and b, either of them vanishes because g vanishes at a and b. So you are left with phi prime g integration over a to b being equal to 0, which means phi prime, by our previous day's result that we have already derived, phi prime must be 0, and if phi prime is 0, then phi is a constant. But that of course assumes that you can differentiate phi, but we are not going to assume that phi is differentiable, we are just going to say that phi is continuous, and that is the reason why we will be invoking the result that we were proving the other day, which we stopped in between because of lack of time the other day. So we will try and complete this, okay. Alright, so here is what we had. We defined M as the average phi x dx, okay, and then we defined a new function phi tilde x as phi x minus m. Yeah, what was the observation we made? We proved it yesterday. Phi tilde x dx integration from a to b, what will this be equal to? 0. Fantastic. Okay. Now notice this is for all g, right, this result. So in general we could have chosen any g, okay, that is a very crucial point, bear that in mind. Now let us look at another object, okay. In addition to this, let us also look at the following. What can you say about this fellow? Well, just invoke this definition here. What happens then? Yeah, so first part of the integration would be simply phi of x g prime x dx a to b minus m integration a to b g prime x dx, isn't it? So the first part is 0 because it is given, right, because of this fact, it is already given to me that this is true, okay. What about the second one? This is simply integration of g prime, which will give you g, and g is a vanishing perturbation, right. So g of a and g of b both individually vanish, so of course g of b minus g of a is also 0, so this is 0 as well. In other words, whatever is true of phi also seems to be true of phi tilde, right? So if this is given to be true for phi and you cook up a phi tilde defined like so, then the same will also be true of phi tilde. Okay, we're just breaking it down into small bits, smaller steps. This much is clear? Alright, so now what do? We have to essentially prove that this phi is going to be a constant. Let's find out if any of these things that we have cooked up can satisfy as a legitimate G. What does a G need to be? It needs to vanish at A and B, and it must be continuously differentiable. So consider the following. Do you remember the differentiation under the integration sign? We'll have occasion to revisit this several times probably today. Guess what's going to be here? Phi or phi tilde, but I'll not use x, I'll use some dummy variable as the running variable here. So phi tilde gamma d gamma. Is G differentiable and continuously so? Why? Because of course if you take the differentiation of this, what happens? First you take the differentiation of the upper limit of the integral and substitute wherever the running variable is there, substitute the variable there. Yes, so it's just 1 times phi tilde x. In other words, G prime is equal to phi tilde, and phi tilde, because phi is continuous, phi tilde is just a shifting of phi by a constant number, so phi tilde is also continuous. Therefore, this G is legitimate. In other words, it is continuously differentiable. What else? G also needs to vanish at A and B. By the very definition, it will vanish at A. Anything you put in here seems to be irrelevant once you've plugged in A here. Basic principle of integration, no? What about G of B? That's exactly what we derived yesterday, no? This is exactly G of B, right? I mean, you can use any running variable here. Instead of x, you can use gamma here, but if you substitute B here, that's B here, that's going to be 0, right? So this is actually a legitimate G. Yeah? Once we have that, what do we do with this? This has to be true for all possible continuously differentiable G functions G which satisfy this property. I've just shown you that this phi tilde which I have constructed here helped me in cooking up one such legitimate candidate G. So therefore, this result that I have shown, which was true because this was true, this was given to me. The moment this is given to me, I know this to be true as well. Now let us just use the same G that we have cooked up here and substitute the corresponding G prime, which would be what then? So let us call this equation number 1. Let us call this 2. What does 1 and 2 give you? So from 1 and 2, substitute G prime here, which is nothing but phi tilde of x. So we have phi tilde of x times phi tilde of x dx being equal to 0. Yes, the first phi tilde is just this phi tilde, the second phi tilde is arriving because of this, which means what exactly? Now that there is a square here in the integrand, if this has to vanish, phi tilde x must be 0 everywhere, which means phi tilde x is equal to 0 for all x belonging to the interval between a to b. But if this is 0, it essentially means that phi x is equal to m, not just any constant but in fact its average value, which is true for any constant function, right? Any constant function is equal to its average value. It's a basic fact. So we have established that indeed whenever you are given this, you don't actually have to assume that phi is continuously differentiable. Just phi being continuous suffices in establishing that phi must be a constant. Now why is this relevant? Is this part clear completely? I hope it's clear. Okay. Yeah. No, but so that's something we'll be using quite a lot throughout. If something has to be true for everything, then it must be true for certain specific examples of that set of everything. Yeah. So if that condition has to be true, it must be tested against all these possibilities, and one such possibility is this. So in case it has to be true for this possibility, then we arrive at a more general condition, right? So that's how we arrive at conditions. No? We have something that's true for a whole bunch of things. You pick out any one from that bunch of things and you test it, it should still be true. Yeah. Okay. Now let's see why this is of particular interest to us, why this is relevant to us. Okay. Let's get back to where we started all this from, which is the first variation being equated to 0. Okay. So we have j of y being given by this. And then we replace this y with a perturbed version of itself, that is y plus alpha g. Yes. So the first variation evaluated at y along the direction of g, what was that? Of course, through that Taylor series expansion, we had written it earlier, no? You have to divide by alpha, right? You have to take j of y plus alpha g minus j of y divided by alpha as in the limit alpha tending to 0. Yes. So what was there? The partial of L with respect to y multiplied by g. So I am just going to omit that for the time being, all these arguments. Plus the partial of L with respect to y prime times g prime. In the earlier situation, what we had done was we had carried out integration by parts on this fellow, right? And we got everything in terms of a common g which we pulled out from the right, and then we use that result that phi times g integrated leading to 0 implies overall continuously differentiable g implies that phi must be equal to 0, and that is how we arrived at the Euler-Lagrange conditions. Now let us do things a little differently. Yes?
The Reymond lemma which you proved right now.
Yeah.
Why does GAGB need to be 0? They can just be equal and.
Why do you think they? I mean, those are perturbations, no? Those are perturbations that must satisfy the endpoint conditions. So you are not looking for arbitrary functions, you are looking for functions which also satisfy the terminal constraints. So whatever they might do throughout the excursion, they have to at least vanish at the endpoints. Okay. So now let us pick out this fellow, okay, for integration by parts. Okay, so a to b partial of L with respect to y times g dx. Okay. So what do we do first? Is equal to, keep the g constant, okay, and what else? Integrate this Ly okay, you can just use some dummy variable here. I might, okay, maybe it's worth writing the arguments at this point. Yeah, you can just use gamma y of gamma. Let's be completely explicit here in the whole description. by something that we've just done, do you immediately see that the derivative of this thing inside the integral is exactly nothing but this? So I'm saying in the integration by parts, this is my u and this part is my dv, right? So integration u dv, again to recall, is equal to uv minus integration v du, where v and u are functions of x. Yeah. So I'm saying now I'm going to keep this u, this is my dv. So if this is my v, do you see that this is indeed dv? Just by something we have shown a while back. This is Leibniz rule of differentiation under the integration sign, right? So this is my dummy variable gamma, and only the upper bound of this integral contains x. So when you differentiate this with respect to x, you do indeed get back, and you substitute x everywhere in place of gamma, you do indeed get back this. Yes? It's just Leibniz rule of differentiation under the integration sign, right? Okay, so this, yeah, and this evaluated at, because it's a definite integral, right? What else? So uv minus integration v du. Now I have to integrate v du. So what is du now? G prime, right? So I have to have a g prime of x here. Okay, let me also put the x here. Okay, sorry. Yeah, g prime x here, and this integration between a to x L of y gamma y gamma y prime gamma d gamma, this whole thing dx. Yes? Agreed? This is all right? Okay, let's substitute this back here then. I'm going to retain the second term as it is, which is just plus integration from a to b L y prime g prime dx. I'm going to just carry on with this shorthand notation here, omitting the arguments because nothing much changes here. What happens to this one? Now there is this g prime that's common to this one as well. Yeah? So there's an integration happening between a to b, and whatever's inside the integration is this fellow, right? So I can actually write this as integration between a to x of L y gamma y gamma y prime gamma d gamma g prime dx. In other words, if I were to pull this out in common here, I can actually eliminate this altogether. Do you see that? Sorry? Yeah, there will be a minus sign, sorry. Yes, thank you. Now, let's simplify this even further to give it the appearance of something more familiar, something that we've just seen. Yes? No difference? Now then, this thing within the second bracket here, if you call this as the phi that we had just been talking about a while back, if you call this as phi, then what happens? This is phi g prime and this is the first variation, right? So the first variation must vanish for optimality. So we already know that this is equal to 0, which means, and g is allowed to be any continuously differentiable function, which means what can be said of phi, the way we have defined this? It's a constant, right? It is a constant. So we have L y prime minus integration between a to x L y, of course with the dummy variable here, y gamma, y prime gamma, d gamma must be equal to a, let me erase this phi here, must be equal to a constant. What does this tell us? The earlier was a pointwise condition, a differential form of the Euler-Lagrange equation. This is the integral form of Euler-Lagrange equation. More importantly, what was bothering us earlier with that differential form? The fact that when you differentiate this fellow with respect to x, what shows up? The y double prime. But you had only assumed that y is continuously differentiable, so you were worried about whether this y double prime even exists or you might be able to do this or not. Now, quite clearly, you see that it's doable because this fellow can be differentiated with respect to x once. This is just a constant. So, of course, this fellow is going to be differentiable with respect to x, come what may. In other words, functions, the extremals that satisfy the Euler-Lagrange condition, they enjoy this special privilege that even if you initially start your search over continuously differentiable functions, the ones that will pop up as a result of solving the Euler-Lagrange condition will also have this y double prime existing. You don't have to worry about it. And this integral form makes it amply clear. That's also the other important thing. This is a condition that's true of the entire path. So it's talking about the global picture in some sense, about the entire curve. The pointwise was just, you take some point and at that point the Euler-Lagrange differential equation is true. That's true of differential equations and integral equations in general, right? So this is the integral form of the same Euler-Lagrange equation. It's as legitimate. Okay, so that's what we wanted to establish, and in the process we proved this other result, the Dubois Reymond lemma that we started yesterday. Because if you want to take the ddx of this, you have to have the y double prime, right? That's what we saw the other day. When you take the ddx, the total derivative of this, then it must be differentiable with respect to each of its arguments, which are x, y and y prime. So when you take it with respect to y prime, you have to have the partial of this fellow with respect to x multiplied by the y double prime. Yeah, and we were doubtful about whether we should be able to do that. We would be able to write it in that fashion, right? Because we had only assumed that y prime exists, but not y double prime. But now you see, because this fellow is differentiable, it's an alternate argument which shows that y, no matter what happens, Ly prime is differentiable because of the fact that it can be expressed like so. And since it can be expressed like so and it's differentiable, therefore y double prime must also be there. You don't have to necessarily impose that assumption a priori in order to arrive at this.